An oil refinery or petroleum refinery is an industrial process plant where crude oil is processed and refined into more useful products such as petroleum, naphtha, gasoline, diesel fuel, asphalt base, heating oil, kerosene and liquefied petroleum gas. Oil refineries are typically large, sprawling industrial complexes with extensive piping running throughout, carrying streams of fluids between large chemical processing units. In many ways, oil refineries use much of the technology of, and can be thought of, as types of chemical plants. The crude oil feedstock has typically been processed by an oil production plant. There is usually an oil depot at or near an oil refinery for the storage of incoming crude oil feedstock as well as bulk liquid products. An oil refinery is considered an essential part of the downstream side of the petroleum industry operation. Raw or unprocessed crude oil is not generally useful in industrial applications, although light, sweet crude oil has been used directly as a burner fuel to produce steam for the propulsion of seagoing vessels. The lighter elements, however, form explosive vapors in the fuel tanks and are therefore hazardous, especially in warships. Instead, the hundreds of different hydrocarbon molecules in crude oil are separated in a refinery into components which can be used as fuels, lubricants, and as feedstocks in petrochemical processes that manufacture such products as plastics, detergents, solvents, elastomers and fibers such as nylon and polyesters. Petroleum fossil fuels are burned in internal combustion engines to provide power for ships, automobiles, aircraft engines, lawn mowers, chainsaws, and other machines. Different boiling points allow the hydrocarbons to be separated by distillation. Since the lighter liquid products are in great demand for use in internal combustion engines, a modern refinery will convert heavy hydrocarbons and lighter gaseous elements into these higher-value products. Oil can be used in a variety of ways because it contains hydrocarbons of varying molecular masses, forms and lengths such as paraffins, aromatics, naphthanes, alkenes, dienes, and alkanes. While the molecules in crude oil include different atoms such as sulfur and nitrogen, the hydrocarbons are the most common form of molecules, which are molecules of varying lengths and complexity made of hydrogen and carbon atoms, and a small number of oxygen atoms. The differences in the structure of these molecules account for their varying physical and chemical properties. And it is this variety that makes crude oil useful in a broad range of several applications. Once separated and purified of any contaminants and impurities, the fuel or lubricant can be sold without further processing. Smaller molecules such as isobutane and propylene or butylenes can be recombined to meet specific octane requirements by processes such as alkylation, or more commonly, dimerization. Octane grade of gasoline can also be improved by catalytic reforming, which involves removing hydrogen from hydrocarbons producing compounds with higher octane ratings such as aromatics. Intermediate products such as gas oils can even be reprocessed to break a heavy, long-chained oil into a lighter short-chained one, by various forms of cracking such as fluid catalytic cracking, thermal cracking, and hydro-cracking. The final step in gasoline production is the blending of fuels with different octane ratings, vapor pressures, and other properties to meet product specifications. Oil refineries are large-scale plants, processing about 100,000 to several hundred thousand barrels of crude oil a day. Because of the high capacity, many of the units operate continuously, as opposed to processing in batches, at steady state or nearly steady state for months to years. The high capacity also makes process optimization and advanced process control very desirable. Major products. Petroleum products are usually grouped into three categories: light distillates, middle distillates, heavy distillates and residuum. This classification is based on the way crude oil is distilled and separated into fractions as in the above drawing. Liquefied petroleum gas. gasoline, naphtha, kerosene and related jet aircraft fuels, diesel fuel, fuel oils, lubricating oils, paraffin wax, asphalt and tar, petroleum coke. Further products include sulfur, olefins, heat and electrical energy. Oil refineries also produce various intermediate products such as hydrogen, light hydrocarbons, reformate and pyrolysis gasoline. These are not usually transported but instead are blended or processed further on site. Chemical plants are thus often adjacent to oil refineries, or a number of further chemical processes are integrated into it. For example, light hydrocarbons are steam cracked in an ethylene plant, and the produced ethylene is polymerized to produce polyethylene. Because technical reasons and environment protection demand a very low sulfur content in all but the most heavy products, it is transformed to hydrogen sulfide via catalytic hydrodesulfurization and removed from the product stream via amine gas treating. Using the so-called Claus process, hydrogen sulfide is afterwards transformed to elementary sulfur to be sold to the chemical industry. The rather large heat energy freed by this process is directly used in the other parts of the refinery. Often an electrical power plant is combined into the whole refinery process to take up the excess heat. Common process units found in a refinery. Desalter unit washes out salt from the crude oil before it enters the atmospheric distillation unit. Atmospheric distillation unit distills crude oil into fractions. See continuous distillation. Vacuum distillation unit further distills residual bottoms after atmospheric distillation. Naphtha hydrotreater unit uses hydrogen to desulfurize naphtha from atmospheric distillation. Must hydrotreat the naphtha before sending to a catalytic reformer unit. Catalytic reformer unit is used to convert the naphtha boiling range molecules into higher octane reformate. The reformate has higher content of aromatics and cyclic hydrocarbons. An important byproduct of a reformer is hydrogen released during the catalyst reaction. The hydrogen is used either in the hydrotreaters or the hydrocracker. Distillate hydrotreater desulfurizes distillates after atmospheric distillation. Fluid catalytic cracker unit upgrades heavier fractions into lighter, more valuable products. Hydrocracker unit uses hydrogen to upgrade heavier fractions into lighter, more valuable products. Visbreaking unit upgrades heavy residual oils by thermally cracking them into lighter, more valuable reduced viscosity products. Marox unit treats LPG, kerosene or jet fuel by oxidizing mercaptans to organic disulfides. Alternative processes for removing mercaptans are known, e.g., Dr. sweetening process and caustic washing. Coking units process very heavy residual oils into gasoline and diesel fuel, leaving petroleum coke as a residual product. Alkylation unit uses sulfuric acid or hydrofluoric acid to produce high-octane components for gasoline blending. Dimerization unit converts olefins into higher-octane gasoline blending components. For example, butane can be dimerized into isooctane, which may subsequently be hydrogenated to form isooctane. There are also other uses for dimerization. Gasoline produced through dimerization is highly unsaturated and very reactive. It turns spontaneously to form gums. For this reason, the effluent from the dimerization needs to be blended into the finished gasoline pool immediately or hydrogenated. Isomerization unit converts linear molecules to higher-octane branched molecules for blending into gasoline or feed to alkylation units. Steam reforming unit produces hydrogen for the hydrotreaters or hydrocracker. Liquefied gas storage vessels store propane and similar gaseous fuels at pressure sufficient to maintain them in liquid form. These are usually spherical vessels or bullets. Storage tanks store crude oil and finished products, usually cylindrical, with some sort of vapor emission control and surrounded by an earthen berm to contain spills. amine gas treater, clause unit, and tail gas treatment convert hydrogen sulfide from hydrodesulfurization into elemental sulfur. Utility units such as cooling towers circulate cooling water, boiler plants generate steam, and instrument air systems include pneumatically operated control valves and an electrical substation. Wastewater collection and treating systems consist of API separators, dissolved air flotation units and further treatment units such as an activated sludge biotreater to make water suitable for reuse or for disposal. Solvent refining units use solvents such as cresol or furfural to remove unwanted, mainly aromatics from lubricating oil stock or diesel stock. Solvent dewaxing units remove the heavy waxy constituents petrolatum from vacuum distillation products. Flow diagram of typical refinery. The image below is a schematic flow diagram of a typical oil refinery that depicts the various unit processes and the flow of intermediate product streams that occurs between the inlet crude oil feedstock and the final end products. The diagram depicts only one of the literally hundreds of different oil refinery configurations. The diagram also does not include any of the usual refinery facilities, providing utilities such as steam, cooling water, and electric power, as well as storage tanks for crude oil feedstock and for intermediate products and end products. There are many process configurations other than that depicted above. For example, the vacuum distillation unit may also produce fractions that can be refined into end products such as spindle oil used in the textile industry, light machinery oil, motor oil, and various waxes. The crude oil distillation unit. The crude oil distillation unit is the first processing unit in virtually all petroleum refineries. The CDU distills the incoming crude oil into various fractions of different boiling ranges, each of which are then processed further in the other refinery processing units. The CDU is often referred to as the atmospheric distillation unit because it operates at slightly above atmospheric pressure. Below is a schematic flow diagram of a typical crude oil distillation unit. The incoming crude oil is preheated by exchanging heat with some of the hot, distilled fractions and other streams. It is then desalted to remove inorganic salts. Following the desalter, the crude oil is further heated by exchanging heat with some of the hot, distilled fractions and other streams. It is then heated in a fuel-fired furnace to a temperature of about 398 degrees Celsius and routed into the bottom of the distillation unit. The cooling and condensing of the distillation tower overhead is provided partially by exchanging heat with the incoming crude oil and partially by either an air-cooled or water-cooled condenser. Additional heat is removed from the distillation column by a pump-around system as shown in the diagram below. As shown in the flow diagram, the overhead distillate fraction from the distillation column is naphtha. The fractions removed from the side of the distillation column at various points between the column top and bottom are called side cuts. Each of the side cuts is cooled by exchanging heat with the incoming crude oil. All of the fractions are sent to intermediate storage tanks before being processed further. Specialty end products. These require blending various feedstocks, mixing appropriate additives, providing short-term storage, and preparation for bulk loading to trucks, barges, product ships, and rail cars. Gaseous fuels such as propane, stored and shipped in liquid form under pressure in specialized rail cars to distributors. Lubricants, usually shipped in bulk to an off-site packaging plant. Wax, used in the packaging of frozen foods, among others, may be shipped in bulk to a site to prepare as packaged blocks. Sulfur, byproducts of sulfur removal from petroleum which may have up to a couple % sulfur as organic sulfur-containing compounds. Sulfur and sulfuric acid are useful industrial materials. Sulfuric acid is usually prepared and shipped as the acid precursor oleum. Bulk tar shipping for off-site unit packaging for use in tar and gravel roofing. Asphalt unit prepares bulk asphalt for shipment. petroleum coke, used in specialty carbon products or as solid fuel, petrochemicals or petrochemical feedstocks, which are often sent to petrochemical plants for further processing in a variety of ways. The petrochemicals may be olefins or their precursors, or various types of aromatic petrochemicals. Siting, locating of petroleum refineries. A party searching for a site to construct a refinery or a chemical plant needs to consider the following issues. The site has to be reasonably far from residential areas. Infrastructure should be available for supply of raw materials and shipment of products to markets. Energy to operate the plant should be available. Facilities should be available for waste disposal. Refineries which use a large amount of steam and cooling water need to have an abundant source of water. Oil refineries therefore are often located nearby navigable rivers or on a seashore, nearby a port. Such location also gives access to transportation by river or by sea. The advantages of transporting crude oil by pipeline are evident, and oil companies often transport a large volume of fuel to distribution terminals by pipeline. Pipeline may not be practical for products with small output, and rail cars, road tankers, and barges are used. Petrochemical plants and solvent manufacturing plants need spaces for further processing of a large volume of refinery products for further processing, or to mix chemical additives with the products at source rather than at blending terminals. Safety and environmental concerns. The refining process releases a number of different chemicals into the atmosphere, and a notable odor normally accompanies the presence of a refinery. Aside from air pollution impacts, there are also wastewater concerns, risks of industrial accidents such as fire and explosion, and noise health effects due to industrial noise. Many governments worldwide have mandated restrictions on contaminants that refineries release, and most refineries have installed the equipment needed to comply with the requirements of the pertinent environmental protection regulatory agencies. In the United States, there is strong pressure to prevent the development of new refineries, and no major refinery has been built in the country since Marathon's Garyville, Louisiana facility in 1976. However, many existing refineries have been expanded during that time. Environmental restrictions and pressure to prevent construction of new refineries may have also contributed to rising fuel prices in the United States. Additionally, many refineries have closed due to obsolescence or merger activity within the industry itself. Environmental and safety concerns mean that oil refineries are sometimes located some distance away from major urban areas. Nevertheless, there are many instances where refinery operations are close to populated areas and pose health risks in California's Contra Costa County and Solano County. A shoreline necklace of refineries built in the early 20th century before this area was populated, and associated chemical plants are adjacent to urban areas in Richmond, Martinez, Pacheco, Concord, Pittsburgh, Vallejo, and Benicia, with occasional accidental events that require shelter-in-place orders to the adjacent populations.